Welcome back to The Explainer. Today, we're jumping straight into the heart of modern enterprise networks. We're going to pull apart a device that is absolutely everywhere, yet honestly, so often misunderstood: the network switch. We'll start by breaking down its foundational mechanics, get a peek at the physical silicon making split-second decisions, and then we're going to take a pretty sharp turn into the high-stakes reality of Layer 2 cybersecurity. By the time we wrap up, you won't just know what a switch does, you're going to understand exactly how it thinks, how it breaks, and most importantly, how to defend it. Here's our roadmap for today's deep dive. 1. Meet the network switch. 2. Inside the switching engine. 3. The MAC learning process. 4. The domino effect. And finally, 5. Layer 2 under attack. Let's get right into it.
All right, Section 1. Meet the network switch.
To truly get why switches are such a massive game changer, we kind of have to look at the exact problem they were engineered to solve. And to do that, we look back at their ancestor, the legacy hub. Think of a legacy hub like a blind megaphone. When a hub gets a data frame, it has no clue who the frame is actually for, so it just blindly shouts that data out to every single port on the network. It's incredibly noisy, it causes a ton of collisions, and yeah, it's a huge security risk. But an Ethernet switch? It's more like a smart intersection. It intelligently directs frames only to the specific recipient's port, creating this beautiful, dedicated collision-free path between the sender and the receiver.
Now, all this intelligence happens at a very specific place in our network model, Layer 2, the data link layer. Switches are specifically designed to connect a massive number of wired Ethernet devices on local segments, giving us that heavy port density that standard routers just can't pull off. But here's the absolutely crucial takeaway. At Layer 2, a switch doesn't understand IP addresses. It's not looking at your IP packets at all. Instead, it reads the physical, hard-coded hardware addresses tucked inside those Ethernet frames. You know them as MAC addresses, to make its forwarding decisions.
Moving right along to Section 2, inside the switching engine. So we know what a switch does at Layer 2, but how on earth does it physically process this massive volume of data at lightning speed? Notice the centralized processing module, and right next to it the memory lookup structure. When a frame hits an interface, the switch doesn't casually ping a software program to ask what to do next. No, it relies on highly specialized hardware chips called ASICs, application-specific integrated circuits, to perform these raw, hardware-level lookups against a wildly optimized memory table. Decoupling the control plane, which runs the protocols, from the data plane, which actually pushes the packets, is the exact secret sauce that allows enterprise switches to crush millions of frames per second.
And that highly optimized memory? It's called CAM, or Content Addressable Memory. Now, normal RAM in your laptop takes an address and hands you back the data stored there. CAM does the exact opposite. You give CAM the data you're looking for, in this case, a destination MAC address, and it instantly hands back the physical storage port where that device lives. It literally searches its entire memory bank in a single simultaneous operation looking for an exact binary match, a 0 or a 1. This instant lookup is the pure magic that lets the switch maintain line rate forwarding speeds without bottlenecking the network.
And hey, while we're on the topic of memory, we absolutely have to mention TCOM, or Ternary Content Addressable Memory. So where standard CAM demands a perfect, exact match for Layer 2 MAC addresses, TCOM gives us 3 potential results: 0, 1, and a don't care state. That don't care state is totally revolutionary because it allows modern multi-layer switches to perform longest prefix matching for Layer 3 IP addresses. Essentially, CAM handles your strict Layer 2 hardware matches, while TCOM steps in to handle the robust, complex routing rules up at Layer 3.
Which brings us nicely to Section 3, the MAC learning process.
Okay, so the memory exists, but how does the switch actually learn where all your computers, printers, and servers are hanging out to populate these high-speed CAM tables? Well, it all happens dynamically step by step. Step 1, the switch receives an incoming frame on a port. Step 2, and pay attention, this is vital, it looks at the source MAC address of the sender and immediately writes that MAC and its physical input port right into the CAM table. Boom, it just learned where the sender lives. Step 3, it peeks at the destination MAC address in the frame and checks its CAM table for a match. Step 4, if it finds a match, it shoots the frame directly to that exact port. But what if the destination MAC isn't in the table yet? Well, in that scenario, the switch is forced to flood the frame out of all other ports in that VLAN. It temporarily falls back to acting like a dumb hub until the target replies, and the switch can finally learn its location. Keep that specific flooding behavior tucked in the back of your mind.
Time for Section 4, the domino effect.
we're pivoting now from how the switch works to exactly how it breaks. You see, the OSI model was designed so that different layers can operate completely independently, without knowing what the other layers are up to, which is fantastic for engineering, but honestly, it's a nightmare for security. Notice the initial compromise happening at the data link layer here. Every single layer above it is completely clueless. Your transport layer, your session layer, your pristine application layer, they all collapse blindly like dominoes. A network security is really only as strong as its weakest link, and on a local network, layer 2 is very often that weakest link.
So why is it such a weak link? A lot of the time, it comes down to a classic cultural divide in IT. Network operations, or NetOps, are laser-focused on keeping the lights on, right? They care about VLAN routing, uptime, and making sure everyone has connectivity. Security operations, SecOps, on the other hand, are focused on boundaries, firewalls, and catching threats at layer 3 and above. SecOps often just assumes the foundational switching layer is, well, just dumb plumbing, leaving them entirely blind to underlying layer 2 vulnerabilities. And trust me, this gap in visibility is exactly what attackers love to exploit.
Let's dig into exactly how they do that in Section 5, Layer 2 Under Attack. Before we see how bad actors exploit the switch's internal memory, we need to quickly dissect a MAC address. A MAC address is a 48-bit hexadecimal universally unique Layer 2 address. The first 24 bits are the organizationally unique identifier, the manufacturer code assigned by the IEEE, telling us if it's a Cisco, an Apple, or a Dell device. The second 24 bits are assigned specifically to that exact physical interface. It's totally unique to the hardware. And as we know, the switch relies on this 48-bit string to build its entire CAM table.
But remember what we learned about that CAM table? It's hardware. It has a fixed physical size. Attackers know this, and they use a brutally simple, devastating tool called MACoff. This script does one thing. It generates random fake 48-bit MAC addresses and just blasts them into the switch at an absurd rate of 480,000 entries per minute. Now, a typical enterprise switch CAM table might max out at roughly 131,000 entries. Do the math. The attacker fills the entire memory bank to the brim in about 70 seconds. Once that table is completely full, the switch can't learn any new legitimate MAC addresses. And what do we say this switch does when it gets traffic for an unknown destination? It floods it. The attacker has successfully overflowed the memory, forcing this incredibly intelligent, high-end enterprise switch to regress and act like a dumb, completely transparent hub. All network traffic is now indiscriminately blasted out to every single port, meaning the attacker can just sit back and quietly sniff up all your sensitive data right off the wire.
And this isn't just theoretical. Look at this terminal output. This is exactly what a catastrophic memory exhaustion attack looks like in real time. You can literally watch the total matching CAM entries just absolutely skyrocket. 36,000, 88,000, 104,000, until it hits the ceiling and flatlines at exactly 131,000. In barely over a minute, the switch's hardware brain is totally paralyzed, and every single packet of new traffic is going to be indiscriminately flooded across the local area network. It's terrifyingly effective.
So how on earth do we stop this from happening? Well, your primary enterprise defense mechanism here is control plane policing, or COP. COP acts as a vital, highly configurable shield. It filters and actively rate limits the traffic destined for the switch's main processor. By implementing strict quality of service policies, COP ensures that a massive flood of bogus MAC addresses or malicious control packets cannot exhaust the system's memory or CPU. It dictates exactly what is and isn't permitted to hit the control plane, keeping the route processor stable and preventing the entire switch from just melting down under the pressure of an attack.
We have covered a massive amount of ground today, from the physical ASICs and memory of a switch, right up to how an attacker can completely dismantle its logic in seconds. I want to leave you with this final, provocative thought. If your foundational Layer 2 architecture, literally the very bedrock of your local network, can be compromised and turned into a leaky hub in just 70 seconds, how secure is the sensitive data sitting at your application layer right now? It's a stark reminder that true enterprise security requires deep visibility and active protection at every single layer of the stack. Thank you so much for hanging out with me for this explainer. Keep learning, keep questioning, and I will see you in the next one.